Namaste students, welcome back to Rama Teaches You. Today we are going to do the last video of classification of elements in the periodic table, the English video. Okay, so in the previous video we discussed, the last topic that we discussed was electronegativity. That is, how can an element in a compound, especially a chemical compound that is a covalent bonded molecule, basically try to attract the shared pair of electrons towards itself. I call it the selfishness trait. The selfishness trait of an element in a chemical bond to attract the shared pair of electrons towards itself is known as electronegativity. Okay, so and we did the Pauling scale. We understood the formula. Okay, we learned how to calculate the electronegativity of one element by comparing it with other element, and the base element that we took for electronegativity was fluorine. Okay, and we gave, because fluorine is the most electronegative element, Pauling. Okay, Pauling gave the element an electronegativity of 4. Okay, the electronegativity is the only property. We have learned three properties, right? We have learned ionization, electron gain, and the third is electronegativity. Ionization and electron gain enthalpies, both of them are a characteristic trait of the element itself. They are a characteristic trait of the element itself, but electronegativity is not that. The case with electronegativity is not that so. Always changes with the partner atom that is connected to it. Okay, for example, chlorine's electronegativity might change when it is in contact with hydrogen, when it is contact with sodium, when it is in contact with calcium. So basically the electronegativity is a relative term. It is a relative term, and the relation is usually done with the partner molecule to which the element is attached. Okay, so let's actually see how the electronegativity varies in a periodic table. The variation of electronegativity in a periodic table is given as follows. Variation along a period. Okay, now we know that as the radius decreases, the electronegativity actually increases, right? Because when you're forming a bond with an atom, the distance between their two nuclei basically matters a lot, right? How much distance you have. If your radius is small enough, then your bond will also be shorter. Therefore, the strength of the bond will become stronger. Okay, so we know that as we go from left to right along a period, what happens? The radius actually decreases. Not only that, the number of protons in each and every single element as we go from left to right also starts to increase. So both the electronegativity as well as the effective nuclear charge is increasing as we move from left to right, and this allows us to say that the electronegativity actually increases as we go from left to right. On moving from left to right across a period, as the effective nuclear charge increases and the size decreases, the value of electronegativity increases due to an increase in the attraction between due to the increase in the attraction between the outer or the valence electrons and the nucleus. Variation along a group. How does the electronegativity vary along a group? Along a group, we know that every single element, one below the other, has an extra shell, right? So the first periodic element will have only one shell. The second one will have 2, 3, 4, 5, 6, 7, all the way from the first row to the seventh row. So here we see that as the element goes down, as we go down the group, the size of the atom is actually increasing because every single atom is being introduced with a new shell. Therefore, basically the distance between the nucleus and the outermost electron actually increases. The radius increases, therefore the electronegativity actually decreases. So, as we all know, fluorine is the most electronegative element, right? Fluorine is the most electronegative element. And we also know what are the elements that are present in the halogen series: fluorine, chlorine, bromine, iodine, acetylene. So acetylene will be the least electronegative element in the halogen group, and fluorine obviously is the most electronegative element in the whole periodic table. Understood? This is how it varies across a this thing group. Now, variation along a group. On moving down a group, as the atomic size increases, the force of attraction between the outer valence electrons and the nucleus actually decreases, and therefore the electronegativity decreases. That's what I just said. Application of electronegativity. Now, this is an MCQ based question or an assertion reasoning based question. Okay, so it if the difference between the electronegativities of two atoms bonded together is less than 1.9, the bond formed between them is predominantly covalent. Understood? So, how do you know whether the bond formed between two atoms is covalent or ionic? You can figure it out by using the Pauling scale and calculate the electronegativity that exists here. If the electronegativity is less than 1 point, is more than 1.9. Okay, so if it is less than 1.9, it is covalent. If it is more than 1.9, it is ionic. If it is exactly 1.9, then it will show both covalent as well as ionic characters. Okay, now we know that various types of chemical bonds, covalent bonds, actually show ionic character due to the electronegative effect. Right? They show the ionic character due to the electronegative effect. For example, H2O, oxygen is slightly negative charge, whereas the hydrogen atoms are slightly positive charge. Okay, next. Thus, electronegativity is directly related to the non-metallic character. Sorry, wait. Yeah, metallic and non-metallic character. Non-metals have stronger tendency to attract the electron, so these are more electronegative. Why do they want to attract these electrons? Why do non-metals want to attract electrons? We know that the non-metals in their outermost shell, they have more than more than four electrons, right? Four or more electrons is what a non-metal has in its outermost shell. Okay, now if we look at the data, we know that if an element has four or more than four electrons, it cannot transfer. It cannot basically transfer and become a cation, which is the property that is used by metals. It can share an electron, right? It can share an electron because it is unable to actually transfer electrons. So non-metals, usually what they do, they want to get that electron as close to them as possible. Okay, non-metals have the ability or the tendency to strongly attract electrons towards themselves. On the other hand, metals, because of their less tendency to attract electrons, generally have low electronegativity. For metals, we have another property known as electropositivity. Non-metals, if you want to define them, you define them by using their electronegativity. You say that metals are very less electronegative, but metals are highly electropositive. Okay, so that is one thing that we will learn more about in the future classes. Okay, hence, an electronegativity increases across a period, the non-metallic character also increases. So if an element is more electronegative, we can say that it is also more non-metallic in nature. If they ask you, if they give you like five or six elements and they ask you to arrange them in increasing order of their non-metallic character, and they have given you the clue of their electronegativity, you can do that by using the electronegativity and arranging them in ascending order. Okay, the least value of electronegativity will be the highest metallic character, and the highest electronegativity will be the highest non-metallic character. Understood? So this is how you can arrange them in increasing order. I hope you understood, Drupad. Did you understand the logic? Okay, let's move on. Difference between electron gain enthalpy and electronegativity. What is the difference? See, basically, why do we want to understand the comparison? Where did the comparison even come from? Both electron gain enthalpy and electronegativity are trying to attract an electron towards itself, right? They're trying to attract an electron towards itself, but they're doing it in two different ways. Electron gain enthalpy is a tendency of an isolated gaseous atom to attract an electron. It should be isolated, it should be gaseous in nature. But electronegativity is the tendency of an atom in a molecule. It is not in a gas. It is not a gaseous isolated atom. It is part of a family. It is part of a molecule, and in that molecule, how it behaves, how much selfishness does it show? That is what electronegativity is all about. Okay, the ability of a atom in a molecule to attract the shared pair of electrons towards itself is what electronegativity means. Now, it is the absolute electron attracting power of an atom. It is an absolute value. An electron gain enthalpy does not change whether who your partner is. Electron gain enthalpy is going to be the same for you wherever you are. But electronegativity is not like that. It is a relative quantity. Because of its relative nature, it depends on how well it can attract partners. That is what electronegativity is all about. Okay, it is a relative attracting power of an atom. Next, it is the property of an isolated atom. It is a property of a bonded atom. That is the main difference. For an isolated atom, your electron gain enthalpy actually works. But you cannot calculate the electron in enthalpy if the molecule is part of a family. It is it can be explained, it can be experimentally measured, it can only be a relative number, cannot be measured experimentally. Okay, and the final part, electron gain enthalpy values of an atom is a constant. Electronegativity of an atom is not a constant. Why is it not a constant? Because it's a relative number, depends on which molecule, which partners a particular element has. That's how electronegativity varies, and this has come in the exam multiple times. This is a 2 marker. Okay, if it's a 2 marker, you can add 4 points, half a point, half a mark for each and every single point. If it's a 3 marker, you will write all the 6 points, all the 5 points. Understood? Is there any doubt here? So electronegativity is what? Electronegativity is the ability of an element to attract a shared pair of electrons when it is bounded together inside a molecule. Whereas electron gain enthalpy is the tendency of an electron to basically attract an electron when it is in its gaseous isolated state. Understood? This is the main difference between both of them. If you can learn how to write this, it will be best. Clear? Okay, let's move on. Periodic trends in chemical properties. Okay, this table will is the summary. Now we are whatever we have learned in this chapter. Okay, we are going to give a quick summary. We have learned after the modern periodic table. Okay, after the modern periodic table, whatever we have learned, we are going to summarize it in a few words. Let's go. So the periodic trends of different periodic properties of elements in the periodic table are shown. Okay, you have the electronegativity, you have the basically electronegativity increases when you go from bottom to the top, right? Because the shell sizes are decreasing, therefore electronegativity goes from the bottom to the top, increasing. Now, the atomic radius is in the exact opposite direction. Atomic radius increases as we go from the top to the bottom. The atomic radius decreases when we go from the left to the right. The electron gain enthalpy actually increases as we go from left to the right. Same with ionization enthalpy. Both of them increase as we go from left to the right. Both the ionization enthalpy and the electron gain enthalpy also increases when we go from the bottom to the top. Because why is it so? Why is it so? Because it is easier. It is easier to attract an electron. It is easier to reduce an electron. Okay, it is easier to remove an electron when you are big. Okay, when you are small, the electron gain enthalpy. What is the electron gain enthalpy? It is the energy released. Okay, Drupad, ionization enthalpy, is it positive or negative? Is the ionization enthalpy positive or negative? Is an electron gain enthalpy positive or negative? Electron gain enthalpy can be positive as well as negative. Okay. Understood? Some elements actually require energy to accept an electron. For example, your this thing, halogen, sorry, the noble gases. And as we all know, the second and the third ionization enthalpies are always positive. Only the first one is negative, even if it's negative or not. Okay, only the first one is going to be negative. The rest of them are going to be positive. Okay, so then the non-metallic character and the metallic character. The metallic character increases diagonally as we go from the top right to the bottom left, and the non-metallic character increases as we go from the bottom left to the top right. So the most electropositive element, the most metallic character will be shown by francium. Okay, lithium, sodium, potassium, rubidium, cesium, francium. Okay, and the most non-metallic character would be shown by fluorine. Okay, the most electronegative and the most electropositive, the most non-metallic and the most metallic character are shown like this. Is there any doubt in this periodic table? Okay, fine. Now, the atomic radii, as we all know, basically it increases from left to right, sorry, right to left, because of the effective nuclear charge increasing and the shielding effect not working that well. Okay, now periodic terms in chemical properties. Okay, from the above discussion, it is clear that the periodic properties play a key role in the study of chemistry of different elements and their compounds. Moreover, these properties also affect the chemical behavior of elements to a very large extent. However, most of the trends in chemical relationship properties of elements like the diagonal relationship, the inert pair effect, the lanthanoid contraction and its effects will be discussed later along with the study of chemistry of different blocks. So, we are in class 12th, you will be learning about the D and F block elements. Sadly, the S and the P block elements have been removed from your syllabus to make your syllabus much more palatable. But it is a very good, interesting topic. The SPDF, every single block we were supposed to learn individually. Okay, next, let's move on. Periodicity of valency or the oxidation state. Valency is the most important characteristic property of an element, and it is defined as the number of hydrogen or the halogen atoms or double the number of oxygen atom that are combined with an atom of an element. Okay, that's what the valency is all about. Understood? What is valency? Valency of chlorine is how much, Drupad? What is the valency of chlorine atom? 1. What is the number? What is the valence electron of chlorine atom? 7. Exactly. The difference between valency and valence electrons is this only. For representative elements, the S and the P block elements, it is generally equal to the number of electrons present in the outermost shell, or equal to 8 minus the number of electrons present in the outermost shell. So, valency of, sorry, lithium, beryllium, boron, and carbon is 1, 2, 3, 4. Then nitrogen, oxygen, fluorine, neon becomes 3210. That's how the valency goes. 1, 2, 3, 4, 3, 2, 1, 0. Okay, next. However, nowadays we don't use the term valency anymore because valency is a very, very old term. Now we use something known as the oxidation state. Okay, oxidation state is a better representation of how a chemical reaction takes place because it tells us how many electrons can be lost, how many electrons can be gained. That is known as an element's oxidation state. Okay, now what is oxidation? It is a process where an element is able to gain an oxygen atom, lose a hydrogen atom, and a new concept, lose an electron. Okay, if an element loses an electron, we say that the element has been oxidized. So, gaining an oxygen atom, losing a hydrogen atom, and losing an electron makes the element oxidized. Is it clear? It makes the elements oxidize. Similarly, losing an oxygen atom, gaining a hydrogen atom, and gaining an electron makes an element reduced. Okay, the oxidation state becomes negative. So if it loses an electron, the oxidation state becomes positive. If it gains an electron, the oxidation state becomes negative. Sodium has an oxidation state of +1. Chlorine has an oxidation state of -1. Calcium has an oxidation state of +2. Oxygen has an oxidation state of -2. Do you see? Can you see what is happening here? Is it becoming more and more clearer? Can you understand what is happening? Okay, so we are going to use the oxidation state much and much more. Okay, so basically from here onwards, we will understand more about oxidation state, most probably in the next chapter and the next to next chapter. We will learn the maximum use of oxidation states will be used in the chapter of redox reactions. Redox reactions are what? A reaction in which both oxidation and reduction takes place simultaneously, and that is a chapter that you need to learn thoroughly for your 11th class examination because a 5 marker directly comes from it. Okay, let's move on. Now, in the two oxygen compounds OF2 and Na2O, the order of electronegativity of elements is fluorine has a greater electronegativity compared to oxygen has a greater electronegativity compared to that of sodium. Now, see, whoever is the more electronegative element will obviously become the anion, right? See, in a game of catching electrons, in a game of grabbing electrons, the person which has a more electronegativity has a better chance to grab that electron and bring it closer to itself, right? So, a more electronegative element will easily become the anion. Are you able to follow me? What I'm trying to say? A more electronegative element will be better suited to be an anion compared to that of a cation. Understood? Drupal? Yeah. Look at the example here. OF2. OF2, there are two elements here. One is oxygen and another is fluorine. Fluorine is the more electronegative element. Therefore, oxygen, even though its electronegativity is the second highest in the periodic table, but fluorine has the highest electronegativity. Therefore, the oxygen atom is forced to be the cation and fluorine atom is forced to be the anion. So that's how I want you to remember it. So the oxidation state of oxygen in OF2 is +2 and the oxidation state of fluorine is -1. Na2O, the oxidation, see, between now the sodium and oxygen, sodium is a more electropositive element and oxygen is a more electronegative element. So here there is no confusion. There is no confusion who is more electropositive or more electronegative. Sodium will obviously become the cation and oxygen will always be the anion. So here what is happening? Na2O. So basically two sodium atoms are required to basically what do you say, compensate for the -2 oxidation state of oxygen. Now in OF2, each fluorine atom with an outer electronic configuration of 2s2 2p5 shares its one electron with oxygen. Being most electronegative, fluorine has an oxidation state of -1. Okay, these compounds may or may not be ionic in nature. I am only saying cation and anion so that it becomes easy for you to swallow. Okay, it becomes easy for you to understand. It could be a covalent bond, it could be an ionic bond. I'm just trying to tell you because oxidation state, you are learning it for the first time. Right, so you need to understand what is oxidation state. I'm just trying to compare it to you with something that you have already learned. Okay, like a cation and an anion. Cation, just like a cation and an anion, oxidation states have plus and minus signs. Okay, you can have +2 or -2 oxidation state. Clear? Any doubts you have, Drupat, please let me know now. Okay. Oxygen with an outer electronic configuration of 2s2 2p4 shares two electrons with the fluorine atom and acquires two. One second. So oxygen's electronic configuration is what? 2s2 2p4 shares two electrons with the fluorine atom and acquires two positive charges, that is its oxidation state in OF2 is +2. Further, in Na2O, oxygen being more electronegative accepts 2 electron from the sodium atom, one from each sodium atom, and hence shows the oxidation state of -2, whereas Na with outer electronic configuration of 3s1 loses these electrons to oxygen and thus exhibits an oxidation state of +1. This is how oxidation states work. The more electronegative element acquires the negative oxidation state, whereas a more electropositive element acquires the positive oxidation state. Okay, the above discussion also shows that oxidation states of elements can be zero, positive, or negative. I want you to tell me whether you understand oxidation states really well or not. Because if you don't, our redox reaction chapter, we won't be able to do it as successfully as possible. So, you know why oxidation states exist? Oxidation states exist because of the electronegativity property that is shown by various elements. Understood? That is where the oxidation state is actually coming from. Understand, Drupat? Okay, let's move on. However, p block elements show more stability for lower oxidation states because of inert pair effect. That is, reductance of the s orbital of the valence shell to take part in bonding. For example, Pb4 plus is less stable than Pb2 plus. Okay, so Pb2 plus has a more stable ions than Pb4 plus because there are some electrons that are so close to the nucleus. We have already learned this in structure of atom, right? There is something known as the penetrating effect. Do you remember what the penetrating effect is, Drupat? What is the penetrating effect? The penetrating effect. The penetrating effect is the property of an orbital. It is the property of an orbital. The orbitals are what? We have various subshells. S, P, D, F are the four subshells that we have. Okay, now these four subshells are arranged in around the nucleus in various regions. The S subshell is the closest to the nucleus in any energy level. Whatever energy level you take, whatever shell you take, the S subshell is always going to be the closest to the nucleus. Then comes the P subshell. Not as close as S, but a little bit far off. Okay, but the D and the F are further away from S. They are further away from the nucleus, right? Their electrons are further away from the clutches of the nucleus. So we say that the s orbital, the s subshell, has a higher penetrating effect, whereas the f subshell has a lower penetrating effect. Clear? Is this clear to you? Did you understand what penetrating effect is? Penetrate means deep inside. Every single shell, the s orbital is the most deeply, the most closely bounded to the nucleus. Okay, so that is the reason why the s electrons of a valence shell do not partake. Okay, the reductance of the s electrons of the valence shell to partake in the bonding. For example, the Pb4 plus is less than Pb2 plus. So lead basically will not give out the electrons from that s orbital, but it will give out from the p orbital. Now for d block elements, maximum oxidation state is n minus 1 d electron minus unpaired plus ns electrons. Okay, so here we can say that manganese manganese is an element that has one of the highest oxidation states ever possible. Okay, manganese, what is the electronic configuration of manganese? Manganese, yeah. For example, 20 is calcium, scandium, titanium, chromium. So scandium, titanium, vanadium, chromium, manganese. The atomic number of manganese is 25. Could you please tell me what the electronic configuration is going to be? Argon 18, argon 18, then 3d5 4s2. So basically there are 7 electrons in the new shell, right? There are 7 electrons that are present in the new shell. So basically it is in the fourth shell there are 2 electrons, and in the third shell the 3d, because they are almost as similar to the energy level of 4s, they are also willing to partake in the chemical reaction. So all the 7 electrons, that is the 2 electrons that are present in the s orbital, and the 5 electrons that are present in the 5 electrons that are present in the d orbital, both of them are willing to basically partake in the chemical reaction, losing themselves from the manganese atom, and thus providing manganese with one of the highest oxidation states ever possible, that is +7. Clear? That is the highest oxidation state possible for any element, and that is manganese, and that is +7. Did you understand what I'm trying to say? Okay, let's move on. So, variation of valencies in the periodic table. How does the valency in the periodic table vary? On moving from left to right along a period, the number of valence electrons increases from 1 to 8. The valency of the element with respect to hydrogen and chlorine increases from 1 to 4 and then decreases to 0. It can be better understood by taking examples of different elements of the second period. We have already different examples of the second period. Now we know that the second period contains what? Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, right? The valency looks like what? LiH. When you take the example of hydrogen, lithium hydride, beryllium hydride, borohydride, carbon, methane, ammonia, water, and HF. Okay, hydrogen fluoride. So what is happening here? The number of hydrogen atoms increases as we go from left to right all the way to carbon. Carbon can accompany 4 hydrogen atoms. Its valency thus is 4. And then nitrogen has 3, hydrogen, oxygen has 2, and fluorine has 1. So as we go from left to right, we see a slight increase from 1, 2, 3, 4. In carbon, you have the highest 4, and then 3, 2, 1, and obviously 0 for the noble gases. Okay, valency with respect to chlorine is also the same. Look at this. Lithium chloride, LiCl, beryllium chloride, BeCl2, borochloride, that is BCl3, carbon tetrachloride, that is CCl4, and nitrogen trichloride, NCl3, Cl2O, and ClF. Okay, these are the, again, what is happening? +1, +2, +3, +4, 3, 2, 1, 0. Okay, again, for the noble gases, it will become 0. That's how the valency varies for the period, for the elements in the left to right. Okay, this is what's happening. But in a group, all the elements have the same valency because they have the same number of outer electrons. The reason we arrange all these elements in a group is why? Because of their same nature of electronic configuration that they have in the outermost shell, right? In a group, all the elements have the same valency as the number of valence electrons are the same in all. Note, transition elements and actinoids also exhibit variable valency, which we shall study later. Okay, now variable valency is the lanthanoids and actinides. We will study that in class 12, D and F block elements. Prediction of the formula of a compound from valency. From the valencies of elements, it is possible to predict the formula of the compound formed by them. For example, if we have an element beryllium and chlorine and want to know the formula of the compound formed by these elements, then first of all, we have to find their valency. Okay, we need to find their valency. Beryllium belongs to the group second element and has a 2 valency. Chlorine belongs to the halogen family with a valency of 1. When these two combine, the formula of the compound obtained will be BeCl2, right? So the valency literally works like this. Beryllium, you write the valency underneath it, and 2, and chlorine, you write the valency underneath it, and then you cross multiply. What do you get? BeCl2. We have learned how to do this in the ninth class, right? The ninth class, we learned how to atoms and molecules, okay, how they combine and all the other stuff. We learned about this. Okay, let's move on. Now, anomalous properties of the second period elements. Okay, second period elements, this is going to be a 4 marker. Okay, so it is a very important topic that you need to understand very clearly. Okay, let's move on. The fourth member of if the first member of each group of the representative element, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine and neon, differ from the other group elements of the representative group. This anomalous behavior is because of their size, their large charge, radius ratio, high electronegativity, and the absence of the d orbital. So this just what does it do? It does something that is very peculiar, that is known as the diagonal relationship. Okay, so instead of sharing their properties with the neighboring atoms in their own group, they share their properties with the elements in the group next to them. Okay, they share the properties with the elements in the group next to them. For example, lithium, beryllium, boron, carbon, sodium, magnesium, aluminum, and silicon. So lithium has a more property sharing with magnesium. Beryllium does that with aluminum, and boron has a similar property that with silicon. So this is known as the diagonal relationship. Okay, the diagonal relationship is a peculiarity that we see. See, basically their valencies are the same. Their configuration is the same. Their values, their compound forming abilities, all of them are the same. But somehow, some of their chemical properties are more relative, are more comparable to the elements that are present in the next group below. This is known as the diagonal relationship. Understood? This is what we call the diagonal relationship. Lithium sharing its property with magnesium, beryllium sharing its property with aluminum, and boron sharing its property with silicon. Did you understand the Trupat? This is known as the diagonal relationship. Understood? Okay, any doubts here? Okay. I'm especially asking this because anomalous properties of the second group is a 4 marker. You will have to explain at least 4 to 5 points, and you have to explain it in detail, extreme detail you will have to go. Okay. Now, what is the reason for this? The reason for this is their small size, large charge to mass ratio, their high electronegativity, and the absence of the d orbital. These are the 3 reasons why they show this anomalous property. Let's move on. Nature of the compounds. The nature of the compounds formed by lithium, beryllium, boron is generally covalent, whereas rest of sodium, potassium, all of these usually form ionic compounds. Why? Again, because they are very small. So the nature of the compounds formed by lithium, beryllium, and boron is generally covalent with compared to the other members of the representative groups predominantly form ionic bonds. Lithium chloride is covalent, whereas sodium chloride is ionic. Again, due to its small size, due to its electronegativity, due to the absence of d orbitals, it is forming covalent bonds compared to the others. Now, maximum covalency. In the first member of each group, only 4 valence orbitals, that is 2s and 3 2p orbitals are available for bonding, whereas for the second members, the number of available valence orbitals is 9. 1 3s, 3 3p's, and 5 3d's. So basically, the reason why they're forming this covalency is because they don't have enough orbitals. They don't have enough orbitals in the outermost shell. Okay, the second period will have 4 orbitals, right? You the first period will only have one orbital, that is 1s. The second will have 4 orbitals, 1s and 3 2p's. Sorry, 2s and 3 2p's. The third period will have 3s, 3p as well as 3d. So a combined total of 9 orbitals will be existing there. Now, this maximum covalency of the second period is only 4. Because, why is it 4? Because it only has these 4 orbitals to share, right? It only has this 4 orbitals to share. That is why it has a maximum covalency of 4. Did you understand this, Drupad? Understood why? Okay, so the members of each group is 4. For example, boron can only form Bf4 minus, but not Bf6 minus, whereas the other members of the group can expand their valence shell to show a covalency of 6. Aluminum generally forms AlF6 3 minus. This is because of the presence of the d orbital. Okay, who is providing them with the extra space? Who is providing them with the extra electron space? It is the d orbital that is doing that. Because aluminum has d orbital, whereas lithium doesn't, sorry, boron doesn't. Therefore, it can only show a maximum covalency of 4. Now, an interesting thing that occurs with the group 2 elements, sorry, period 2 elements, is that they can have multiple bonds with each other. See, multiple bonds is what? Multiple bonds is like the double bond or the triple bond. Okay, double bond and triple bond to form, the next chapter we are going to learn more about this. For them to form, you need a sigma bond and a pi bond. Okay, you need a head-on collision and a sideways overlap. I know these words might seem a little bit odd to you, but trust me, in the next couple of videos, you will learn more about covalent chemical bonding. Okay, and you will understand what these terms actually mean. So, to form a pi bond, the orbitals should be next to each other. It should be able to overlap each other. There should be a sideways overlap. But if the atoms are too big, if the atoms are far apart, usually a double bond is not possible. Okay, the double bond or a triple bond is not possible. Because of their small size and high electronegativities, the first members of each group of the p block show a large tendency to form pi-pi multiple bonds with its own atoms like carbon and nitrogen, or with other atoms of the same period too, like nitrogen and oxygen. Okay, and nitrogen and carbon. This is known as the cyanide group. Okay, CN is called the cyanide group, nitrogen and oxygen, as compared to the subsequent members of the group. Understood? Understood? They can form a double bond. Next, periodic tense and chemical reactivity. So, we are going to summarize. Now we have reached the summary section of the chapter. We are going to summarize again what all we have learned here. Now, we shall now try to explore relationship between the fundamental properties like atomic and ionic radii with the ionization enthalpy, electron gain enthalpy, and valency. We have already done this. Okay, the ionization enthalpy is the least for alkali metals because of their large size in the respective periods, which occupies the left corner of the periodic table. Thus, these elements have a high tendency to lose an electron to form a cation, and this tendency increases as we go down the group. Okay, why does it increase as we go down the group? Because the electrons that are getting added are being added into a new shell. The new shells are further apart, therefore the hold that they have with the nucleus of their own atom actually starts to decrease. That is why the ionization enthalpy decreases as we go down the group. Thus, alkali metals are highly reactive metals, and their reactivity increases on moving down the group. The halogens, which occupy the extreme right in the periodic table because of their high electronegativities, electron gain enthalpies, have high tendency to accept an electron to form an anion, and this tendency decreases on moving down the group. Thus, halogens are highly reactive nonmetals, and these reactivity decreases on moving down the group. So, the ionization enthalpy decreases down the group. The electron gain enthalpy also starts to decrease down the group. Okay, can I ask you a small question, Drupal, regarding this? Could you please tell me, is lithium more reactive, or basically francium or cesium more reactive? Both of them. Lithium and cesium both belong to the alkali metals group. Which of them is more reactive? Drupad? Why is, yes, the answer is correct. Could you please tell me the reason too? It's lower down in the group, so what happens? Why is it more reactive then? It's a larger atom. What happens when you have a larger atom? Okay, so the exactly, because its outer electron is attached very loosely to the atom via the nucleus. Therefore, the ability for the nucleus to actually lose this electron is very, very high. Therefore, it is more reactive as compared to that of lithium. Okay. Next, the chemical reactivity of an element is represented by its reaction with oxygen and halogens. However, here we shall only consider oxides. The normal oxides of elements present on the extreme left are also most basic. We know that, right? In metals and non-metals, we have already learned the fact that metals usually form basic oxides, right? And when you react a basic oxide metal with water, you get a base, right? Sodium oxide, when you react it with water, you get what? Sodium hydroxide, right? So metallic oxides are usually basic in nature and non-metallic oxides are usually acidic in nature. For example, your carbon dioxide. Carbon dioxide is a non-metallic non-metal, right? It is basically non-metallic oxide. Carbon oxide. Carbon is non-metal, therefore it is a non-metallic oxide. What do you observe here? We observe that for a non-metallic oxide like carbon, when you put that in water, that's what an carbonated drink is, right? It becomes an acid. So non-metallic acid, and that acid's name is carbonic acid, H2CO3. So a non-metallic oxide is acidic in nature. A metallic oxide is basic in nature. Okay. Now, there are some oxides that show acidic and basic character. Could you please tell me at least two examples of these oxides that are amphoteric in nature? Do you remember the amphoteric principle? Aluminium and silver. Aluminium, zinc, and silver. These are the three examples that we learned in class 10th. They form amphoteric oxide. That is, basically, they can react as an acid in the presence of a base, or they can react as a base in the presence of an acid. They have dual characteristics. The amphoteric oxides show the acidic and basic characteristics. They behave as an acid with a base and as a base with an acid. Next. Okay. On the other hand, the neutral oxides have no acidic or basic properties. Oxides of the elements present in the center are generally neutral. For example, carbon monoxide, nitrogen oxide, nitrogen dinitrogen monoxide, etc. are amphoteric. Al2O or amphoteric Al2O3 and As2O3. What is As, Drupad? As is arsenic. Okay, it's arsenic. Now, Al2O3 plus 6HCl gives you AlCl3 plus H2O. So, a base plus an acid is giving you salt and water. Again, Al2O3 plus NaOH gives you NaAlOH whole twice, NaAlOH the whole 4 plus H2O. Okay. Now, this is what, how is aluminum oxide behaving here? It's behaving as an acid. Thus, in short, it can be said that across a period from left to right, the acidic character of oxides increases, whereas the basic character decreases. So the oxide of elements that are present at the center, the oxide of elements that are present at the center usually have the ability to form what? Both acids and basic oxides. They are known as amphoteric oxides. You can actually see a transition of oxides as we go from left to right, that is from basic all the way to acidic. Okay. However, on moving down the group, the acidic character of oxides decreases because non-metallic character decreases, whereas the basic character of oxides increases due to the metallic characters increase. Now, Drupal, I have told you that as we go from top to bottom, the metallic character actually increases, whereas when we go from the bottom to the top, the non-metallic character increases, right? Metallic character increases when we go from the top to the bottom. But when we go from the bottom to the top, what happens? The non-metallic character is increasing. And if your non-metallic character is increasing when you're going from the bottom to the top, what happens? What ends up happening? Your acids. Look at this. That's what they are saying here. However, on moving down the group, the acidic character is actually decreasing. The acidic character is decreasing because what is happening? Because the non-metallic character is decreasing, whereas the basic character is increasing because the metallic character is increasing. So the metallic character is actually providing you with the acidic property, and the non-metallic character is actually providing you with the basic property. Sorry, I said it exactly opposite. Okay, I said it the wrong way. Metallic characters increases the what? The basic property. The non-metallic characters increase gives you what? The acidic property. So as we go from top to bottom, the acidic character, does it increase or decrease? As we go from top to bottom, does the acidic character increase or decrease? Huh? Acidic character. So, what is happening, Drupad? Look at this. On moving down the group, the acidic character of the oxides decrease. Who is providing you the acidic character, Drupad? The acidic character is being provided to you by the non-metal. Can you agree with me on this? The acidic character is being provided by the non-metal. You can agree with this, right? Now, the non-metallic character decreases as we go from top to bottom. Okay, therefore, the acidic character should increase or decrease when you go from top to bottom. It should decrease. The metallic character is increasing. The metallic character provides you with the basic properties. Therefore, the basic character of an oxide actually increases as we go from top to bottom. Did you understand these four lines? This could be an MCQ. These four lines, I could make an MCQ from this. Okay. Okay, next one. Electropositive character or metallic character. It is a tendency of an atom to lose its outermost electrons to form cations. It generally increases as the ionization enthalpy decreases. Thus, it is highest for alkali metals and lowest for the halogens. Okay, so the ionization enthalpy is highest for how what? Highest for alkali metals and lowest for halogens. On moving down the group, the electropositive character or the metallic character increases due to the decrease in ionization enthalpy. The transition elements, however, are less electropositive than group 1 and 2 because of their lower ionization enthalpy. So, now, do you remember me telling you in the beginning that from left to right, the elements are transitioning from metal to a non-metal? That is the reason why we call the middle element the transition elements, right? So basically, they have a lower ionization enthalpy compared to that of the group and 1 and group 2 metals. Okay, so electropositive character or metallic character does what? The electropositive character or the metallic character decreases as we go from left to right, whereas it increases as we go from on moving down the group, the electropositive character or the metallic character increases, right? Increases down the group, decreases from the left to the right. Electropositive character is the metallic character. Understood? Electronegative character is the non-metallic character. Okay? So electropositivity or your metallic character, they are synonymous with each other. Understood? They are synonymous. Electronegativity and non-metallic character is synonymous. Clear? Clear, Drupad? Okay, let's move on. Now, electronegativity character or the non-metallic character. It is the tendency of an element to accept electrons to form anions. In general, it generally increases along a period from left to right and decreases on moving downwards. So the non-metallic character increases from left to right and decreases from top to bottom. Oxidation and reducing properties. Reducing properties depends on the tendency to lose electrons, that is electropositivity or metallic character. Whereas oxidizing property depends on the tendency to gain electrons, that is the electronegative or the non-metallic character. The more metallic character you have, the more reducing power you have. The more non-metallic character you have, the more oxidizing power you have. Why? Because oxidation means losing an electron. Reduction means gaining an electron. So a metallic character will do what? It will lose an electron to someone else and it will act as a reducing agent. A non-metallic character will do what? A non-metallic character will gain an electron and basically make the other person oxidize. Therefore, it will act as an oxidizing agent. One second, Drupal. So, in the periodic table, the reducing power property increases down the group, whereas the oxidizing property decreases down the group. Alkali metals are strong reducing agents, while halogens are strong oxidizing agents. The increasing order of reducing character of alkali metals is sodium, potassium, rubidium, and cesium, and the increasing order of oxidizing character is iodine, bromine, chlorine, and fluorine. Understood? So, if you have more electropositivity, you are a better reducing agent. If you have more electronegativity, you are a better oxidizing agent. Clear? What I said, does it make sense? If you have more electronegativity, you are a better more electronegativity, so you are a better what? Oxidizing or reducing agent. More electronegativity, therefore a better reducing agent. If you are more electronegative in nature, you have the ability to take the electron from others, thus you are a better oxidizing agent, right? Similarly, if you have more non sorry more electropositivity, yeah, if you have more electropositivity or a metallic character, what do you have more? You have a large amount of what? Large what? Reducing agent. You are a better reducing agent, Drupad. Okay. Did you understand this or not, Drupad? I have asked you this twice. Did you understand this? Huh? I'll repeat it again. Yeah, once. I'll repeat it again. The whole thing. Okay. So think about this. What is happening here? Now, when do we say that an element has been oxidized or reduced in terms of electrons? If an atom loses its electrons, we say that it has been oxidized. If an atom gains its electrons, then we say that the atom has reduced itself, right? So, how do you take electrons from an atom? Okay, if you have a more electronegative atom, if you have a more electronegative atom, it can easily take the electrons from another element. It can easily take the electrons from the other element. So, what happens then? If you can easily take the electrons, what happens? Your oxidizing ability, your ability to oxidize another element actually improves. So a more electronegative element, a more non-metallic character element will be a better oxidizing agent. Similarly, a more electropositive element, a more metallic character having element will be a better reducing agent. Why? Because it has the ability to give off electrons, right? Metallic character means the ability to give off electrons. Therefore, a metallic character one will have a better reducing ability, whereas a non-metallic character one will have a better oxidizing ability. Did you understand this last paragraph of this chapter? Okay, let's move on. Okay, so we have officially finished this chapter. We have finished the chapter in like 4 videos. Okay, so Drupad, do you have any doubts in this chapter? Okay, so I'm ending this video. I hope you really like my video. And if you like my video, please do like, share, and subscribe. And tell your friends who are preparing for their exams, who are preparing for their half yearlies. If they have any doubts, they can always watch my videos. And if you have any questions, if you want me to explain a topic again, you can write them in the comments, and I will see that. And I'll see you in the next video. Thank you.